Hi everyone, welcome back to Chem Help ASAP. Today we're going to talk about kinetics, and specifically we're going to go through some reaction mechanics. Let's get started. The first thing that I want to talk about is something called molecularity, and this is how a reaction occurs, and you can think of this more as what has to collide for a reaction to take place. And there are several different types of molecularity. So let's go through each of them. The simplest is the unimolecular reaction. This is simply some reactant just going to products. Our rate law would look really simple. It's just K times our concentration of A. So our unimolecular reactions are most often decomposition reactions. So for example, if we had calcium carbonate, it decomposes into calcium oxide and carbon dioxide. Because we only have one reactant, this is a unimolecular reaction. Now let's talk about bimolecular reactions. As you can guess, this means we need two things to collide. And there are two different ways we can think about this. So we can think about A plus B going to products. That would give us a rate of K times the concentration of A times the concentration of B. Or we can think about this as two molecules of A colliding to give us products. And again, that would give us a rate of K times A squared. There are plenty of examples of bimolecular reactions. One example of an A plus B is carbon plus oxygen going to carbon dioxide. Finally, let's talk about trimolecular reactions. So in these reactions, of course, we have to have three different molecules colliding with each other to form products. And again, just like the bimolecular reactions, there are a couple different ways that this can happen. You can have A plus B plus C going to products. Of course, that would give us a more complex rate law, as you see right here. But more commonly, these trimolecular reactions tend to be A plus B going to products. That gives us a little bit simpler rate law where we have A is going to be squared. An example of a trimolecular reaction is two carbon monoxide molecules reacting with an oxygen molecule to give us two carbon dioxide molecules. And if you like, instead of putting a 2 here, to make it look more like this reaction, you can write carbon monoxide plus oxygen going to two CO2 molecules. Now that we have molecularity defined, I want to talk about some other terms before we jump into reaction mechanics. So first, let's talk about what an elementary step is. So an elementary step is a reaction whose rate law can be written from its molecularity. Of course, we just talked about molecularity, and we just showed how all of those rate laws are written simply from molecularity. Next, let's define an intermediate. So an intermediate is anything, any species, but it must be formed and consumed during a reaction sequence. So what this means is that when you're looking at an overall reaction, you do not see the intermediate. It's not a reactant, it's not a product, because it's going to be formed and then consumed. Finally, let's talk about our rate determining step. So this is going to almost always be your slowest step when you have a reaction mechanism that is multi-step. Okay, so let's define these terms in the context of an example. So here is an overall reaction given right here. First, let's see the elementary steps to give us this overall reaction. So here we have two steps. We have our K1, or our first step, and then our K2, our second step. These two reactions are our elementary steps for this overall reaction. Next, let's find an intermediate. Again, this is a species that is formed and consumed during our reaction sequence. We should not find it in our overall reaction. So you'll notice that NO3 right here is formed in our first step, and then it is consumed in our second step. It is nowhere to be found in our overall reaction. So NO3 is our intermediate for this reaction mechanism. Finally, let's determine our rate determining step. Again, this is pretty simple. It's just the slowest step. in a reaction mechanism. So for our particular mechanism here, our first step is our slow step, so it is our rate determining step. Next, I want to talk about how do you determine if a proposed mechanism is correct? Well, we have two criteria that we're going to use. So let's take a look at those. So the first criteria is that the sum of the elementary steps must give the overall reaction. This makes sense, right? The second requirement is that the mechanism must agree with the experimentally determined rate law. So you need to know what your data says the rate law is, and then make sure your mechanism matches up with that. So let's go through both of these requirements again for this overall reaction that we started with in the previous slide. So let me label this. This is our overall reaction. And we're also given the experimentally determined rate law right down here. So the first thing I'm going to deal with is our first requirement, that the sum of the elementary steps must give the overall reaction. So I am just going to write my two elementary steps right here. Again, these were shown on the previous slide. If I add these two reactions together, do I get my overall reaction? Well, the rules here when adding two reactions together is that if you have the same species on the same side of the arrow, either the left or the right, they are going to add together. If you have species that are on the opposite sides of the arrow, they are going to add out. So you can think of these very much like algebraic expressions. So the first thing I see is I have my intermediate NO3. It's on opposite sides of the arrow, so it will add out. I also see another species that's going to add out. It's not an intermediate, but it is my NO2. I have one NO2 molecule on the right-hand side. I've got two on the left-hand side, so simply one of them will add out. Next, I check, does anything else add out? I don't see anything else adding out or adding together, so let's see what we have as our final reaction. So I'm going to bring my single NO2 down. And I also have a carbon monoxide here on the reactant side, so I'm going to bring that down as well. That's it for the reactant side. Now let's see what I've got on the product side. So on the product side, I have an NO or a nitrogen monoxide. I'm going to bring that down, and I have a carbon dioxide. I'm going to bring that down right here. So this is the reaction that I get when I add my two elementary steps. And it's pretty obvious that yes, it does match with my overall reaction. So the first requirement for my reaction mechanism has been met. Yes, the sum of the elementary steps give the overall reaction. Now let's check the second requirement. So now I'm focused in again here on this experimentally determined rate law. I need to make sure that my mechanism matches this rate law. This is where we're going to bring in the concept of our rate determining step. So again, here are my two elementary steps. Because my first step is my slow step, this one is going to be my rate determining step. So very often in these reactions, we monitor the formation or the consumption of an intermediate. So looking at my first elementary step, my slow elementary step, my rate of formation of NO3, again, which is an intermediate, is simply going to be the change in concentration of that NO3 versus time. But remember the definition of an elementary step. An elementary step is a step that we can write the rate law based on its molecularity. Well, what is the molecularity of this first step? It is simply our rate constant, K1, times our reactants, which is going to be NO2 times NO2. This is a bimolecular reaction. Well, another way to write this, of course, is to, instead of writing the concentration of NO2 twice, we just make it NO2 squared. And with that, you can see that we have shown that the mechanism does agree with the experimentally determined rate law. So we proved requirement 1 in the previous slide, and now we have also proven that the mechanism does agree with the experimentally determined rate law. So this reaction mechanism is a valid mechanism for our overall reaction. I hope you found this video helpful, and thanks so much for watching.